Okay, cool, great. Yeah, it was first time to doing a a talk from an iPad. Hey, hi. I'm computer scientist at Argonne National Lab. My team is the MPICH team. We build MPICH for most of our time. So to begin with, a little bit background about MPICH. So MPICH is a high performance implementation of the MPI communication specification, if you would. So it's been developed by Argonne and UIUC for the past 30 years. And so in MPICH, what we aim to do is we have a philosophy that we want to build a MPICH ecosystem. It's essentially a big MPICH family. The way that we do this is MPICH is the open source library that everybody can use, and our vendor partners would use our open source code and for their development and add on their own optimization for their hardware or their target customers, and ship them as the vendor MPI implementations. So in the meantime, we also have a close collaboration with the software libraries and tools team to make sure that MPICH and the MPICH derived MPI application works well with them. So we have moved to use OFI for our lower level communication 7 years ago. So the reason that we choose OFI is largely because it provides a diverse support of different hardwares, and through this common Libfabric API, we'll be able to support MPICH on different hardwares and utilizing the hardware accelerated communication features such as native hardware tag matching and hardware accelerated collectives. So today, the MPICH is following a layer structure where on the top of it is the MPI layer, which handles all the machine independent code, including collectives, management of communicators, and data type handling. And below that, we have a what we call a abstract device, CH4. So the CH4 essentially is handling all the details for the communication when to use, for example, when to use a shared memory transport between two processes or when to use communication. And below that, we're relying on Libfabric and also UCX for the actual communications. So MPICH, the latest MPICH release was MPICH 4.1, which has been released a few months ago, earlier this year. There are several major new features and improvements have come in, and I'm going to talk some of them. So MPIX stream prototype is one of the big effort that we're pushing to provide a better support for not only MPI plus GPU, but generally MPI plus X hybrid programming scheme. And we also have now a separate standalone PMI library that gets released and can be built separately. And we other than these two, we have improvements in the test suite and CI setups and minor fixes to the data type engine. So MPICH, since MPICH 4.0 has a support for GPU. So what MPICH today can do is, if you have communication using a GPU buffer, you can put it in your MPI call. MPICH internally will look at what the data type and what kind of the buffer this is, and what hardware feature is available. So based on those informations, MPICH would decide whether this communication will go through the native data path, where the data being moved from the GPU memory to the network without having the making a copy into the host memory first. And this is also works for internal communication, where multiple GPUs can talk to each other through a GPU direct IPC. So if with MPI, the user can always create some complex data types and non-contiguous data types where may not be able to handled by the network hardware directly. So in this case, we also create a fallback path um, for handling that kind of communication. Essentially, data being packed into a contiguous buffer, and that contiguous buffer can in turn be used can in turn utilize things like GPU direct RNMA for communication. So on the right hand side, this is the latency that we measure using this is on summits actually with CUDA CPU, and it's showing really good latency. So in addition to the capability of moving data from GPU memory, we added this new concept called MPICH stream. So this is still our proposal to the MPI forum for better support for acceleration. So the idea is we can use MPICH stream to represent a serial execution context. So this serial execution context essentially can be something like a GPU stream, where GPU would schedule and execute asynchronously with respect to the host CPU. Or this serial execution context could also be a CPU thread, where it's running on CPU, but might be on different core and might be asynchronous to your main thread. So in either of this case, what the user can do is you use these MPICH stream to create this MPICH stream object to represent these streams. The benefits with that is when you're using this stream, and you can in turn create what we call a stream communicator. Essentially, what this does is when you create this new communicator, MPICH internally can reserve different communication contexts for each of these execution streams. So in the multi-threaded context, this essentially is providing each of these threads a individual network context. This could be implementation-wise. This could be Libfabric scalable endpoint or something else. But the benefit is that since everyone is using their own communication conduit or pipe, if you would, there will be no contention between these threads or these serial contexts, and we'll be able to achieve a very high scalability with increased number of threads. So here's just a quick example showing. So the red line here is traditional MPI without any special optimization for threading, for multi-threaded communication. Now, in that case, if we want to scale the communication with multiple thread, what we ended up with is not higher, but actually much lower message rate because of the contending for the same communication contexts. So the green light here is what we have previously called a multi-communication context. Essentially, this is creating multiple contexts for multi-thread environment and use a round robin fashion to map them. So the user doesn't need to provide information about whether these some of the communication happens on the communicator is from different thread or not. We can try to guess. As long as the user is using different communicator, we try to assign different contexts. So as you can see, the green line is achieving much better scalability in terms of message rates. But still, there's a case where we have more communicators being allocated than the number of contacts that we can create. So some kind of sharing is causing the slightly it is limiting the how much performance we can get. And the green line here is the new MPICH stream implementation. Essentially, instead of implicitly guessing and round robin assign threads to different contexts. In this case, we're basically just reserve some of the contexts and assign them to the specific threads. So there will be absolutely no sharing of anything between each other. So there's no contention at all, which will be able to get the maximum performance that we can achieve on the testing platform. So that's the improvement that we have from MPICH. Another major development work effort that we did in the 4.1 releases is the refactoring of the PMI. As you may already know, that's when you go to run an MPI application, you probably start by MPI-EXEC to launch your application, and the MPI-EXEC will go to create a process on each of the computer node and start your user application. So that job launching and process management is all part of these PMI library, which in MPICH this is a component called Hydra. So historically, we've been using PMI 1 version, and that's a default protocol that's MPICH and Hydra and many of the third-party process management library is using. But at the same time, we also have a PMI 2, which was slightly improved, but was mostly experimental. The original idea was we published some paper, but we never switched to use PMI 2. But because it's part of the open source code, so people start to use it. So Cray supports PMI 2, and also Slurm documents PMI 2, but only supports PMI 1. So there's a lot of complexity and the inconsistency between these. So so what we do is we refactoring a lot of the code and clean up the implementation. And at the same time, we're making the Hydra as an independent tool that can be released and can be built separately from MPICH. The reason is that some other programming frameworks such as OpenSHMEM would also need the capability of launching multiple processes, and in many cases they will try to use MPI execs. So in this case, if by allowing Hydra to be independently distributed and built, it will be it will hopefully simplify the job of all those applications. And along with these refactoring, we also have new options to indicating what is the underlying OS OS library for scheduling and job launching is. So these are the details on that. So that's so far for the 4.1 release. And what we're currently working on is the 4.2 series. And we the target for this is of course by having a beta release by SC this year, and having the GA release by early next year. So there's many new features that is planned, but I'm only going to cover 2 of them in this talk. The first one is called MPIX thread communicator. So the MPIX is just the prefix for all the non-standard MPI implementation. So this has nothing to do with the MPIX stream, but the thread count here, the original idea was we trying to provide a way to simplify the inter-thread communication that that within in parallel region. So our idea is now instead of we can create a thread count and indicating how many threads are in there, and then when an application goes into a parallel region, the thread count we can do a thread count start indicating that we're in the parallel region, and then within that region, all the communicate you can use MPI communication functionality like MPI send and MPI receive, I send, I receive, the same way you use it with processes. But in this case, the communication can happens both at the thread level or at the process level if you're using the thread count. So if the communication happens, if there's two threads talking to each other, the communication would actually happens in basically a load store between the threads, and only when it's off the node they will actually go to the communication network. The benefit of this is from the application developer or library developer's perspective. So, for example, if you're maintaining a math library and you're using MPI for scale out to multiple nodes, but in reality, you have no control whether your user is going to use this with just processes or MPI plus thread hybrid programming. Right. So you ended up need to maintain maybe two versions of code. One of them to be thread safe and handling all the additional synchronization that need when that thread's introduced. So with the thread communicators, we can essentially you can essentially ask the user, say, hey, if you're using thread, you create a thread communicator, and I'm going and put that communicator to my library, and from the library's perspective, just take one communicator and doing the same type of communication on it, and it completely ignoring the detail of whether there's intra-thread communication happening or not. So far, this is open PR on our GitHub, and we have some implementation for point. We have support for point functionality. So both blocking and non-blocking are there, and we have support for all the blocking collectives. Although each of these only have one collective algorithm available, so you don't have the choice between like recursive doubling or others. So there's only one supported, but if this turns out to be needed, we can certainly add more. But there are other functionalities such as non-blocking collective that is on the plan but haven't been implemented, and also we haven't done anything about the RMA for this thread count yet. Okay, and lastly, this is something new that started earlier this year. So as you may know, that MPI world essentially have two. The MPI standard defines what the API looks like, but it doesn't have a standardization on the API, the binary interface. So what it ended up with, a lot of our vendors MPI like Intel MPI and Korean MPI, which build on top of MPICH, are API compatible with MPICH. Means you can build with Korean MPI, build your application with Korean MPI, and linking with Intel MPI, it will work, right? But at the same time, if you build your application with Korean MPI and try to link it with OpenMPI, it will not, because OpenMPI and the MPICH family doesn't have a compatible API. This is has been a pain point for many of the users over the years, and Perform now started a new working group to address this issue. Essentially, we're trying to provide a a compatible ABI between a standardized API that that all the MPI implementation can use, and in that way, the library can be universally interchangeable. All right, so essentially in the MPICH, our plan is we're going to first we're going to keep all the existing non standard API implementation, but at the same time we're providing a different set of new API and new toolchain. So if you don't care about the API, you can still use the MPICC and link to the lib.mpi.so for your application. And if you so everything business goes normal on that department. But if you need you want to have the API, then we provide this MPICC API and also libmpi.api.so for you to use. So with this library, it's going to be using the standardized interface. So we have a prototype implementation for this already, but at the same time, because this is ABI thing is mostly planned for MPI 5 standard, so the standardization would come later, hopefully quick. And but if you're interested in if you try our MPICH today, you can use this and prepare your application for the future. All right, so that's all I have from the MPICH side. I'm happy to take any questions.
Okay, do we have any questions on this? I don't see any questions in chat. That seemed to go very well from your pad there. That worked out pretty well.
Yeah.